Welcome to Hot Chips 22. Session 2, SoCs.
Good afternoon, everybody. My name is Christos Kozirakis from Stanford University, and I'm glad to chair the SoC session. So we've got 4 very exciting talks to wake you up after lunch, 2 of them on some really cool SoCs, and 2 of them on enabling technology that I'm pretty sure we're going to discuss over the next break. So the first talk is going to be about the new SoC for Xbox 360, and we're going to have 2 speakers, one from Microsoft and one from IBM. The first speaker is Rune Jensen, who is an engineering manager at Microsoft. He's been there since 2004 after being for a while at Silicon and Software Systems, Philips and Reshape. The IBM speaker is Bob Dremel, who is a senior member of the technical staff. And he's been at IBM for a while, since '85, and he has worked on a large number of IBM servers, ranging from I-Series, P-Series servers, and Blue Gene.
Thank you, Christos. The title of our talk is the new Xbox 360 250GB SoC, where we have integrated the CPU and GPU functionality. The first slide shows an overview diagram of the system. We have a combined CPU GPU module. You see the CPU on top. It's connected to the graphics core. Historically, that was done via a front-side bus or an FSB. We have now replaced that with programmable logic on chip, and it's an on-chip connection to the graphics core. The die has a GDDR3 memory interface. It has a PCI Express interface to our custom Southbridge I/O chip. It has a video output, again, to a custom display controller chip. And on the module, but as a separate die, we have 10 megabytes of embedded DRAM. The custom chips are done out of the Microsoft Mountain View office in conjunction with our development partners. Further noteworthy system features are we have a 250GB hard disk connected via our Southbridge I/O chip. We have integrated 802.11n wireless, and we have the same system features as we had on prior chips in terms of ODD and flash and various I/O connectivity. We launched our Xbox 360 in 2005. At the time, we started out with 90 nanometer versions of the CPU and the GPU, and they're shown here. We then migrated to 65 nanometer technology in 2007 and 2008. And here today, we are proud to talk about our 45 nanometer version, which we are in mass production with here in 2010. The motivation for doing the SoC integration with cost and power savings. We could reduce the area by removing the front-side bus. We could get the 2 chips into a single package, which is shown here. And we can take advantage of the latest IBM 45 nanometer SOI technology. Further motivation is to simplify our console design, reduce motherboard footprint, simplify the power delivery, and make enhancements to the thermal design in terms of enabling a single heatsink and a single fan solution. When you take the lid off the package, the module is shown in the lower right. You can see the integrated large die on top, embedded DRAM at the bottom. And we got 14 decoupling capacitors for supply decoupling on the module.
The features of the integrated CPU and GPU SoC are the same as previous versions. There are no changes to the architecture. Both Microsoft and IBM have presented this architecture at previous conferences, so I'm sure this combined block diagram looks familiar. I will very briefly highlight the key features. For the CPU, 3.2 gigahertz PowerPC cores with a 1 megabyte shared L2 cache. For the GPU, 48 parallel unified shaders with a high-speed I/O interface to the 10 megabyte EDRAM on the 2-chip MCM. One significant area of change was the front-side bus, or FSB. When we combine the two chips, we remove the driver-receiver I/Os and PHYs for this interface. For backward compatibility, we then needed to insert new logic, referred to as the front-side bus replacement, or FSBR. The latency and bandwidth of the FSBR matches prior versions. This is a topic I'll discuss in more detail on a future chart. This diagram illustrates the floor plan of the SoC, with the key blocks from the previous page highlighted. You can see the 3 CPU cores, the L2 cache, the graphics core, the high-speed interface to the EDRAM, and the front-side bus replacement. Here are some of the chip statistics. The chip is in 45 nanometer SOI with 10 levels of metal and contains 372 million transistors. There are 153 different array types and approximately 1,000 instances of those arrays. There are approximately 1.8 million flip-flops or latches and multiple PLLs and multiple clock domains. Compared to the 2005 CPU-GPU combination, this SoC has reduced power consumption by more than 60% and has reduced area by greater than 50%. The package is a 35 millimeter flip chip PBGA with a 323 stack up. The 2-chip MCM contains the combined CPU-GPU SoC and the 10 megabyte EDRAM. As in past CPU designs, the SoC utilizes an adaptive power supply with multiple power domains. And finally, the chip is manufactured by IBM and one alliance partner. The dual nature of the combined chip, a high-performance CPU and a high-density GPU, provided our greatest challenge. We needed to combine a semi-custom, high-performance design methodology with a high-density, ASIC-like one, as described in this chart. The resulting enhanced methodology enabled us to combine the two disparate elements. Let me begin with the GPU on the right-hand side of the page. We started with the GPU Verilog. This is IP we were unfamiliar with. We wrote conversion scripts to modify the Verilog to insert our IP, primarily infrastructure, or what we at IBM call pervasive. This includes our test logic, our clocks and clocking structure, latches or PLLs, arrays, IOs, and PHYs. And then convert the Verilog to VHDL, which is the language we were most familiar with using. We utilized our 12-track, high-density ASIC library, along with a global array subsystem and common IP. We leveraged our placement-driven synthesis as well as gate-level timing and a combination of clock grids and a clock tree to close timing on the GPU. On the CPU, we utilized a semi-custom design methodology that we were very familiar with. First, a little background. We designed the first Xbox 360 CPU in 90 nanometer SOI. That chip was largely a full custom design. We then migrated to 65 nanometer SOI, taking advantage of technology and area power reductions. That design still contained custom elements, but also contained more synthesized macros. The migration to 45 nanometer continued to take advantage of technology and area power reductions, and this design contained even more synthesized macros, hence the semi-custom terminology. On the CPU side, we utilized our 18-track high-performance base library, which is also used in several of our other server chips. As I mentioned, the design still contained custom elements, but also contained custom macros. We utilized transistor-level timing and a full clock grid over the CPU to close timing. Finally, we integrated the two portions into a single chip, utilizing a hierarchical design methodology, including verification, timing, and test. The resulting chip from this enhanced methodology met our cycle time and functional goals on DD 1.0. A couple of metal-only tapeouts cleaned up a small number of lab issues. A few comments about the chip. Our games back into line, 10 levels of metal, had the right balance between density and performance, while wiring the GPU was still a challenge. As I mentioned, clocking across the chip is primarily a grid with a few small clock trees on the GPU. Since we were unfamiliar with the GPU, we made as few changes as possible there, primarily infrastructure, but we did make significant changes in the front-side bus. That final comment leads into my last chart. We made all the changes that I've been discussing in these previous charts. We updated the clocks and the clock gating logic. We inserted our test logic. We inserted new latches and flip-flops, PLLs, IOs and PHYs, arrays. How do we ensure we didn't break something? How do we ensure backward compatibility? By backward compatibility, I mean we want this new hardware to be transparent or seamless to the user. To be transparent or seamless, the new hardware must have the same performance and function the same. The strategy we used was a combination of sequential equivalence using an IBM tool and new and existing pattern-based verification. Here's our definition of sequential equivalence. Compare corresponding sequential path outputs from two different design representations to ensure their function is the same. Here's a simple example. Take one of the shader units on the GPU, for example. Using sequential equivalence and formal techniques, stimulate the inputs on that shader unit in both the original and converted versions and ensure their outputs are the same. This provides both performance and functional validation for units that don't change. We have used this tool on past CPU migrations. It's been used extensively within IBM, and we extended it to the GPU on this project. To complement or supplement sequential equivalence, we used existing pattern-based test cases to verify functionality. For any areas of change, we wrote new test cases, particularly the pervasive logic and also the new front-side bus. We have found that this combined strategy is extremely powerful and valuable for design migrations. As I mentioned before, the resulting chip from our enhanced design methodology and validated with this combined strategy met our cycle time and functional goals on DD 1.0 with high quality.
one of our key design requirements was to optimize power. I'm going to describe two of the techniques that we used and the resulting improvements. We use adaptive power supply for our core logic. Historically, the SRAMs have been the limiting factor for reducing the core supply. For that reason, we had a separate SRAM supply, and you can see the results here. For the core VDD, we are able to operate between 0.83 and all the way up to 1.15 volts, while on the SRAMs, we supply between 1.2 and 1.3 volts. So not only does that enable us to harvest yields from a very wide process window, from very slow to very fast processed part, it also gave us great power saving. You can see the number here of 31%. Another technique we use is in-system voltage regulator calibration. The required voltage for the chip is stored in e-fuses on the die. When we build our system, we supply the voltage via VR11-based regulator. It has about 2% tolerance on the load line and 2% tolerance on other voltage parameters. We use a ring oscillator-based on-die measurement and compare the in-system measurement of the ring oscillator speeds with that stored by the ATE. That allows us to calibrate out the tolerances, and we get a saving of about 12%. And in total, that gives us a 43% power saving. When we measure our maximum power, we have developed a power application called the so-called power virus, where we combine maximum CPU and GPU power. That has been designed to be more aggressive than games, and it's at least 10%, but in most cases, as you can see here, it ends up being 15 to 20%. So while that can seem as an overkill, it also provides us adequate headroom, as well as improved thermal and acoustics performance, which I'm going to discuss in some of the following charts. Another key design requirement is that we must meet the maximum hotspot and average die temperatures. And that's regardless of CPU or GPU workloads. So the way we solved the problem was to create power maps and then associated thermal maps for our most extreme use cases of max and min CPU and GPU power. We did these power maps using the slowest silicon, as that has the largest thermal gradients across the chip and does provide the most conservative situation for our analysis. The analysis showed some good spots for a hotspot diode as well as an average temperature diode. The hotspot is between two of the CPU cores, and the average temperature is measured by the GPU shaders. We have a separate diode for the EDRAM, however, that's always running cooler than our larger combined CPU-GPU parent die. The thermal algorithm uses the diode measurements to regulate the fan speed and thus the system temperature. We run the chips close to the maximum temperature. The goal is to keep the fan speed low. However, we cannot get too close to our maximum because there are thermal situations in the system that lead to a thermal overshoot. As an example, when you transfer from a low power mode to a high power mode, then you can get a thermal spike, in our case up to about 6 degrees C. So our set points have to allow for those kind of conditions. To do that in an efficient manner, we reduced the set points in low power mode, and with that, we were able to achieve that all thermal requirements for the chip was met. The results from the power and thermal optimizations are shown in this diagram here. On the y-axis, we show the fan speed as a function of the power here on the x-axis. The blue line shows a console operating in a 25 degrees C ambient temperature environment. And you can see, even for high power games, we are at about 35% or so fan speed. Most people would perceive that to be somewhere between a quiet library or a quiet home from a noise perspective. As the ambient temperature increases, in a hot summer day in California, you may see maybe a 35 degrees C ambient temperature environment. While the fan speed naturally has to increase, we still have adequate headroom. And most people would perceive the noise from the fan to be at the level of a quiet home, or in case you're in low power mode, playing a movie, it would be perceived like a quiet library environment. The console design with the combined chip had several advantages. First and foremost, we were able to reduce the power and with that have a smaller power supply unit. We have a simplified motherboard design, as is illustrated on the right-hand side. Up high, you can see the existing Xbox 360 motherboard, and here the motherboard with a combined CPU GPU SOC. In green, it's illustrated where the two chips and the corresponding front-side bus was in the past design, and here's the new design. In blue, you can see the power delivery comparison between the two different solutions, and with that, we were able to achieve a substantially smaller motherboard design. Having just one significant chip from a power perspective to cool gave us great thermal flexibility. We could put an oversized heatsink in the console. You can see it there with the copper slug. We have a fan on top of that, and the ODD is beside it, and between the fan and the ODD, now you have the width of the new console, which is shown here with the hard disk on top. And wrapping it all together, we have a great console size reduction, and here we show the new Xbox 360 250 gigabytes console. So in conclusion, we have presented the first high-performance integrated CPU GPU SOC. We have 372 million transistors implemented in IBM 45 nanometer SOI technology. Based on the power and thermal optimizations that I illustrated on the past charts, we have enabled a very quiet console design. And these benefits were achieved by doing close collaboration across chip development and system design teams. And that concludes the talk. Thank you.
We've got time for a few questions, so please state your name and affiliation.
Bill Rash with Intel. And my question is regarding the design choice to keep the embedded DRAM as a separate die. IBM is offering an embedded DRAM logic process at 45 nanometers. So what drove your decision to keep the embedded DRAM on a separate die?
We did the cost trade-offs, and it was advantageous to keep it as a separate die. So.
Okay, that seemed like to be an excellent application for embedded DRAM, okay?
Nathan Brookwood, Inside 64. Another question on the embedded DRAM. Is that a custom chip, and is it using the same sort of embedded DRAM technology that IBM is using in its Power 7, or can you add us some color on that?
We can do that. It is a custom chip designed out of the Microsoft team in Mountain View with our development partners. The actual eDRAM cell itself is a different design, but it could be replaced with the deep trench decap that IBM have been known for. It has a small amount of logic on that chip for depth processing, and that is essentially to minimize the amount of data transfers across the high-speed I/O interface. So does that answer your question?
That was helpful, thank you. And second question, you mentioned the speed of the CPU, but you didn't mention the clock frequency for the GPU, and how do you deal with the different clock domains for those parts?
Well, there's a number of clock domains on the GPU. You know, the main frequency is 500 megahertz, and we have multiple PLLs.
Okay, thank you.
Hi, I'm Bo Marr from Raytheon. I was wondering how much of the process going to a new technology node was automated?
I think, as you can tell from my talk, more and more is becoming automated, correct? As we're able to synthesize more elements and have fewer custom elements.
So did that change the, I'm not sure if this is proprietary, but did that change the pricing at all, or reduce the time frame at all from, I imagine it would, from the ASIC and semi-custom design design cycles?
Yeah, so we can't comment much about pricing and stuff, but obviously doing the semi-custom implementation made it much more straightforward from a manpower perspective and a development time perspective to implement the chips. So that is one of the big advantages as we go to 45 nanometer for this design here. The CPU efforts became essentially less.
So I guess, can you talk about the percentage that maybe had to be redone and the percentage that was automated? Or is that proprietary?
I didn't understand, hear the question.
The percentages that were redone and percentages that were automated, I think that's proprietary. I don't think we have the specific information for this one here.
All right, well, thank you.
Dean Takahashi from VentureBeat. How much time did it take to do this one, and how many people did you have on it, especially compared to the original teams?
We can't comment on the development times and the staffing levels, but you can see we've been producing the new chips within about a 2-year cadence. But the exact levels and the time for this, we can't comment on, unfortunately.
And then I guess let's see how. What drove the schedule for this as well? Like, was there a particular thing that drove it above just getting it done as soon as you could?
Well, we try to get our chips done and out to market as soon as possible. There are big events like E3 where we announced this console here. I think people were happy when we were able to have the chip in place and the console in place in time for that.
Let's thank our speakers again.
Thank you.
Okay, so now we're going to switch from the SoC in your living room to the technology behind the SoC in your pocket. So the next talk is titled Extensions to the ARMv7-A Architecture. And the speaker is David Brash, who is an architecture program manager at ARM. He's been there since '98, and he is chairing the architecture review board. In the past, he's been with Raycel and with Digital Equipment Corporation.
So these switch on.
short intermission. We can use this for you to acclimatize to my European accent. I think the guy from Google's left, so you'll have to do the translation locally. Hey. Okay, my name's David Brash. I'm in the architecture group at ARM. And it gives me a lot of pleasure to be here today and announce some new additions to the ARM architecture. So I think most people here will know that we are pretty pervasive as an architecture in many markets now. It's evolved to meet various needs, and when we came out with V7, we actually introduced 3 profiles. A, R, and M, I was extremely skeptical about using these different letters, I must admit, when the marketing people came up, but it has actually helped us segment where A's applications with virtual memory, R's are real-time areas such as in disk drives, and M for microcontrollers, and we've got a huge amount of scaling in the architecture across different needs. We're concentrating on the A profile today, and really, again, the other point is this is an extension of where features have been initiated on mainframes, they've evolved to the desktop, and now in things like the ARM architecture, low power, mobile environments, we're starting to see architecture features become more and more appropriate there. And so it's a logical extension for us today. So what we'd like to announce today, this is the first public sharing, is a virtualization extension where we are introducing a new privilege level for the hypervisor and various features, 2 stages of translation to complement what we have in the architecture today. And secondly, a large physical address space. We're finding pressures on the 4 gigabyte arena, particularly in physical memory with cameras, etc. And so this should ease the pressure over the coming years. I'd also like to introduce a couple of other little concepts related around the interrupt controller. It's really an announcement. We're also bringing out, we'll be putting information out there on the generic timer architecture, and we're doing some work on system MMU as well. So I think this slide summarizes very well what virtualization is and just shows how well established it is. Really, the software is executing an environment that it thinks it's in real hardware. The hypervisor needs the controls and the security to keep virtual machines apart. And the user needs the responsiveness, the performance, etc., and characteristics of an underlying machine and not see the difference. A couple of other comments on terminology. We're talking about an abstraction here where the virtual machine monitor or the hypervisor is acting as a proxy for these different virtual machines. And there's 2 forms of virtualization. Full virtualization, where there's complete binary compatibility with running in the real hardware, or para-virtualization, where there is some interaction between the hypervisor and an API that modifies that underlying operating system, sometimes for performance reasons. Or, as in the current ARM architecture, it's actually essential to do that on current parts. So what have we done about it to bring it into the ARM architecture? So as I've already mentioned, we've introduced a new hypervisor mode that sits with a higher level of privilege above the kernel. The whole intention here is to minimize the interruption and the overheads associated with that hypervisor, and where it has to, we want to trap the hypervisor where it has to trap the hypervisor. So the guest OS does its own table management. We have 2 stages of memory management. We've also made some changes in the interrupt controller to minimize the overheads there and allow the guest OS to do as much handling as possible and as much independence for the device drivers. Syndrome support. It's also when you do trap to a hypervisor, you want to know where you've come from and what the cause was in as efficient a means possible. So we've done some extensive use of syndromes, which are in the status registers, providing lots of information on the exact reason for the trap and a lot of control for the hypervisor on what it traps, so that different environments need different amounts of trapping. And finally, when you're in the hypervisor, you've potentially got to switch the context. And those of you familiar with the ARM architecture will know that it's a modal architecture with lots of bank registers, and that to access them you had to move between modes. What we've introduced here is, in the system instructions, the ability to get at those bank resources and copy them just from the hypervisor without any switching at modes or an additional overheads. And the virtualized ID register facilities is, IDs are typically read-only resources, and some of these are now read-write capable such that the hypervisor can mimic different devices, different features for the underlying virtual machine. So just a slide on what the current situation is in the ARM architecture today. And we actually have a security extension where we run effectively two address spaces with a secure and a non-secure space. You have the user and privilege for the kernel split. And illustrated down the bottom is the trust zone monitor. It runs in the secure side, but has access to the non-secure side. And this is the means of doing transfers across this environment. It can be used for forms of virtualization, but there's no other real provisions in acceleration. And there's, when you're using the interrupt model, our recommended model for this is using what we call fast interrupts, one of the bank modes for the secure side, and Auricchio standard interrupts for the other side. I'll come back to that later when I talk about interrupt controllers, because it's the more flexibility that the architecture is introducing there. And as mentioned, we've introduced a new level of privilege on the non-secure side in terms of a hypervisor mode, and now it has the ability to use that to switch the context from an OS to one or more guest OSs. So moving on to the features we've added for virtualization. I think we've already mentioned the hypervisor mode. There's a rich set of trap options, whether it's for TLB or cache management. Talked a bit about the ID groups and various classes of instructions. So load store is an obvious example where you potentially need to trap, and obviously a lot of the privileged control instructions as well. The SYNDM register is a 31-bit register, and it's this constant form. So there's a class field to indicate which class of trap you're in. There's an instruction length field. Again, for those of you familiar with the ARM architecture, in thumb state, it's a mixed length instruction size, 16 and 32 bits. So we need to know what the length of the instruction was in some cases that when trapping. And then further information, whether it be to do with memory management or the type of trapping associated with ID groups, etc. The other key features is that we now have a dedicated link register. Again, for those of you familiar with the architecture, the link register R14 is one of the general purpose registers, and it's actually shared between doing procedure calling and exception entry and exit. However, when you introduce virtualization, you now have a situation that you could trap on a function call, and if you did that, you would lose architectural context. So what we've done is we've introduced a separate exception link register and a dedicated instruction of ERET for returning from that exception. And this is how we've resolved that issue for virtualization in the exception model. And finally, in terms of the features, moving on to address translation, I mentioned at the start we've introduced this large physical address. This is actually a compulsory component for support of virtualization, but can be used as a single stage of translation in its own right with a bigger address space. And we'll be moving on to that in the next few slides. In terms of the address translation, the key piece that's been added is the two levels, with now a virtual translation table base as illustrated in the top line. And in terms of the operating system, we've previously had two base registers. It'll be illustrated in the following slide how we use those, and that stays the same. There's a separate translation for the hypervisor so that it can run its own virtual address environment. And finally, the secure side can do virtual to physical translation. We don't have hypervisor capabilities there because the whole reason for our rationale when we introduced the security extension was for heavily certified code, and the idea is to keep that small, which is counter to introducing hypervisors and more complexity. So just to illustrate the address translation, this is just showing the two stages. The first stage owned by the operating system, second stage owned by the hypervisor. And a couple of points to make here is that clearly in an implementation, the TLBs that are used can merge these two stages together. And so we don't expect people putting in TLB banks for both, although there are various caching techniques that people can put into the microarchitectures to help minimize overheads. And the other point is that the faults are disambiguated. I think I've sort of mentioned before with the amount of trapping we do. We can trap to the operating system, we can trap to the hypervisor, and the hypervisor's got a lot of control over what it allows the operating system to see directly. So moving on to the actual large physical address, and just looking at the first stage. It's managed by the OS. We've moved to 64-bit descriptors. We're doing a larger address space, you need more bits. 512 entries per table, and the key thing here is table size of 4 kilobytes is now the same as the page size. This is common to many other architectures. Operating systems like the flexibility of structures being the same size, but in the ARM architecture, as it stands today, we actually require 16 kilobytes for a level 1 page table, and so you need effectively 4 pages of contiguous memory. So that's been simplified by this mechanism for the operating system's demand page management. I mentioned we have 2 translation table bases for the user kernel. Again, the previous architecture, there was a threshold as to which address boundary this came in within our 32-bit address space. As we move to a larger address space and we're supporting up to 40 bits, we can grow them from top and bottom with size registers, and any unmapped memory will fault. Unmapped addresses will fault. If you do the maths in this, it means that with the size of page table entries, etc., and the size of tables, we retire 9 virtual address bits per level, up to 9. For 32 bits of virtual address, it's 2 bits at level 1, and then you have 9 bits at level 2 and level 3. And finally, for terms of the actual page table entries themselves, now 64 bits with a large portion dedicated to doing the address. The lower attributes are very similar to what's been done in the architecture today, supporting the classic memory types, caching policies, shareability, etc. And the upper bits, there's a couple of new features have come into the architecture. One is we've introduced a privileged execute never, such that now user code, especially things like JITs, which can be modifying it, you can now manage through a policy that it allows the user to execute, and the privileged environment, it will not execute in that environment. We've also got the ability for these some table override bits, so that as you're walking down the hierarchy, you will always walk the full hierarchy to resolve the address, but there are some bits that can act as override bits, and so it's easier to manage if you actually want to temporarily change a policy around permissions, etc. You've got the advantage that you can do with some bits higher up the hierarchy. I think the only other point to make there is with contiguous hints and blocks, we've also put in the ability there for 16 entries within a table. They still need to be populated, and they still need to be managed when managing TLBs by address. But if you put in the hint, this is effectively saying these are contiguous, and the TLBs can use it for efficiency and effectively put 16 pages into a single entry. Moving on to the second stage, which is managed by the hypervisor. It is the same table walk mechanism, so it's all shared within the regime. There are a few differences, because at this level we do imagine that people will be managing memory in a coarser fashion. You have to be able to resolve down to 4 kilobytes for things like virtualizing I/O, but in general, memory will be allocated in much larger chunks. So what we have allowed in this instance is, in our 3 levels of walk, is that we can have 2 contiguous page tables at level 1, and we can have up to 16 at level 3, and I've got an illustration in the next slide as to how that can affect things. I've just realized actually that there's a small error there, and I managed to modify the slides wrong because I modified the next slide instead of knocking that one out. Anyway, my apologies. So, as I mentioned before, one table base and page table entry, very, very similar. The upper attributes are somewhat simpler for this second stage of translation. So just looking at the way the walks happen for a second stage, you would have up to 40 bits of IPA, and you will effectively, you can use either one or two tables at the front, you're then picking up to 16 tables and then moving down. If you're using the 16 tables, you can get the benefit of 34 address bits in 2 stages of walk and don't need to use the extra overhead of the third stage. So that concludes the discussions on the main parts of the architecture, and hopefully giving you a summary of the features. I mentioned earlier that in terms of the interrupt controller, we made some changes here as well. So ARM did standardize an interrupt controller about 2 years ago now, particularly when we started introducing some multiprocessing into our architecture. It was seen as a good time, and our microcontrollers took advantage of this. So we have a very common programming model between our microcontroller line and this architecture. It logically splits into 2 blocks. One is a distributor, which is kind of, I would say, almost static features, so the types of interrupts, where they're allocated, their underlying priorities. And then a CPU interface, which is managing things like the interrupt acknowledge, ending the interrupt, priority masking, etc. So these 2 logical blocks within the interrupt controller. I should also mention that in our security extension, the ARM architecture has historically had 2 modes or 2 vectors for handling interrupts called IRQ and FIQ. And within our security extensions, we've recommended that people would use the FIQ for secure interrupts and the IRQ for normal interrupts. And they have a hierarchy within the architecture as well, which fits well with that general policy. In the version 2 of the architecture, we're adding support for virtualized CPU interface. So now the physical interrupts will trap to a hypervisor, and then the hypervisor will build lists against the virtual machines. And what that is also allowing us to do is to virtualize both the IRQs and the FIQs within our base architecture. Probably the easiest way of doing that is to just discuss it in the next diagram, which is fairly busy, but this is the interrupt controller as it stands today. And part of the feature set is to actually group interrupts into 2 groups, and those registers residing within the distributor block. And group 0 interrupts would then can optionally be enabled to be on the FIQ, and so that signal goes to an ARM processor, and they'll be handled as on the FIQ entry point, and the other interrupts on the IRQ. But if you remember earlier with the exception model, we've now got a situation where if the OS is wanting to use FIQs, it's potentially competing with secure interrupts and a secure handler. So really it's a situation where a system designer has to use one model or the other if they're wanting to use the 2 interrupt types. What we're announcing today, and the extensions to the interrupt controller to support it, is that the group 1 interrupts are the ones that always effectively non-secure and go to the hypervisor, and the hypervisor reintroduces the concept of the group 1, group 0. Now, all this is transparent to the CPU because that part is effectively a virtual distributor. The hypervisor will trap in setting up those conditions, but once executing, the virtual CPU is seeing FIQs, IRQs at the guest OS level transparently, just as if it was running in real, excuse me, as if it was running in real hardware. And the real hardware can allow the guest to use both, obviously, if it's not using the secure thing. But now we've got an ability for secure software using physical FIQs and an operating system using the other 2 classes. In terms of a system MMU, not a great deal to say. This is just a very simple diagram that modifying the memory management system within a core is not the whole story. And if you want to virtualize I/O in particular efficiently, you need to put a system MMU out in the system, and we're working on one of those. And that system MMU can be either no translation, you can offer stage 1 or stage 2, or you can offer both levels of translation. It will be the same page table format, so we'll be sharing the page tables with the ARM cores, and it relates the context. So the context within our memory management has both VMIDs and ACIDs. For the architecture specification for this will be published in the first half of next year, and ARM is planning to support it in ARMvs, and that's the only bit of sort of Marcom I'm going to do around that. Other point is that generic timers, and this is really just a piece of sort of advertising architecturally, we are introducing them. They will be in the same specification. Low latency access from our system control CPUs, so consistent model of time, supports both up and down styles of counter, and we've got a virtual offset for those that require it, and to support virtualization built into the architecture. So I was going to show something here, and I didn't realize the time had did a jump on me, but the hypervisor boot flow, we're coming down the secure side. We always boot on the secure side. We move across into a hypervisor. You can now build an operating system and switch between the two. So that's a generic picture. And sort of now moving into the closure. So in the ecosystem, made this announcement today. We will be providing a specification as preliminary data this quarter. We won't have it fully reviewed, otherwise it'll be fully released this quarter. Our first implementation is very well advanced. It's codenamed Eagle. That name has been out there. And I believe TI, one lead partner that I know that's announced themselves as supporting it. And you certainly expect to hear a lot more about that this year. We're very, very close to releasing that design. The third-party engagement as well, just a list of people I've been personally involved with, at least 3 of them, in terms of getting hypervisors done. So we believe we've got a robust architecture here done in conjunction with these parties. So in summary, as we see, it's a natural progression for the ARM architecture to move into this domain. There's all the classic uses in servers, and we think there's going to be places for low-power servers with the ARM architecture, various other uses, but also opportunities for new cases. So in a place like Stanford, I think it's an ideal kind of venue for stimulating people's thoughts, and maybe there's some new uses for virtualization and low power. Thank you.
Hi, I'm Eric Metzger. I had a question on your instruction support for virtualization. Are you suggesting that you have like a control structure and then specific instructions to interface that control structure for your virtualization support on Eagle?
There's very few additional instructions. There's just the one instruction for doing the exception return from the new mode, because of, as I mentioned, the link register, and then we've added these means of reading these coprocessor registers into the regular register set without chopping and changing modes. So they're the main changes. There are some more system registers, obviously, but they just really build on the standard ARM architecture.
Okay, so there's no specific control structure for the virtualization going in and out of the VMM or hypervisor?
Nothing specific. It's all built. It's just built logically on top of the memory management, adding a new privilege level.
Okay.
Bill Rash, Intel Corporation. You mentioned that you have both para-virtualized and full virtualization under development. Could you explain some more what kind of application or difference in features would take you toward a full virtualization implementation versus the para-virtualized implementation? Okay,
well, I believe that certainly the architecture can support full virtualization at the operating system levels now, but some of the situations around making efficient hypercalls for device drivers, there's a case for especially if you wanted to share resources. There's cases where para-virtualization still makes sense in drivers. Not my area of expertise, but then talking to various hypervisor vendors, it's not quite as simple as you've got an architecture that can fully virtualize everything, so the answer is to fully virtualize everything. But certainly we expect to be able to run the operating systems, and we are running operating systems with no change. But areas like drivers for shared resources is one area where we anticipate people to still use para-virtualization techniques.
Okay, thank you.
Shubha Mukherjee, Cavium Networks. One of the issues I've seen both with ARM and with MIPS is that when you guys specify the virtualization specification, you limit yourself to the processor core. Unfortunately, the rest of the system hangs loose because a lot of the stuff that you guys do in the specification specifies in the core, the rest of the IO system or the IOTLB, IOMMU, all the management has some dependence on the core itself. So have you guys thought about when you're actually talking about creating a virtualization specification, what it means to virtualize a coprocessor like an encryption engine, or to virtualize an IO device like a disk, and what support the processor would need to provide?
Your question really touches on what we've done, well, first of all, on the interrupt controller to try and ease the overheads with that, but also it goes into the system MMU domain. Now, we do envisage that our first, in fact, I can say our first system MMUs will require software management independent of what's being done within the cores and the cluster of cores. But we can envisage in the future broadcast structures and sharing as the kind of coherency model and all these features extend out and across the fabric.
So that means the other question is on that side is you're not requiring SRIOV compliance for supporting IO virtualization?
We're still in our infancy around all the IO virtualization, to be truthful. So it's a stage thing. And as I say, right now, those familiar with ARM will know that we've got some cores today where we have system caches, level 2 caches that are memory mapped rather than controlled in a hierarchical fashion. The architecture supports hierarchy, but all our cores, there's a mix there. There's probably an analogy here for system MMUs where we start to do more, but certainly initially it will be system managed in conjunction.
Thank you.
Hi, Kevin Parmenter with XR Corporation. On one of the slides you had a little block that said something about power control for the IC, and I'm curious if that's something that goes on isolated on the device, or if that's, like we've seen on the other presentations, intelligent communication with the power system externally.
I'm trying to think what I put in the slides around power control, but the one thing around power control, in fact, I think it was touched on earlier in the IBM presentation, is we think that virtualization lends itself to doing where the proxy agents will be for a lot of power control. So we are doing a lot of work, not in just context switching of virtual machines per se for running multiple virtual machines, but also thinking about if you want to run that and potentially swap that virtual machine from one processor onto a different one, which may have a different power profile. Our background is in low power processors, but as you build more and more capable processors, you've still got this tension as to what minimum power they can have when they're still power efficient. And we actually see a place for multiple CPUs, not necessarily of identical microarchitectures, but you would start switching there. So that's one area around power management where this work will overlap. Certainly, we're not adding straight features into the core architecture. I think you'll see very similar structures with ARM partners around separate microcontrollers, etc., that we saw in the IBM presentation.
Thank you.
Thank David again. So now I'm going to switch from the ARM-based systems in your pocket to the chips that you can actually talk to them in base stations. So the next talk is on the Transcede SoC by Mindspeed Technologies. And they're going to tell us about how they solve the 4G challenges for Pico, Micro, and Macrocell platforms. The speaker is Jim Johnston, who is the CTO at Mindspeed for their media and wireless business. And before Mindspeed, he's been at Connexent and Rockwell.
Thank you very much. Thank you for having me here. I'm going to go through a presentation a little bit different. Starts out with some network architectures and then eventually gets into the SoC architectures. So this probably doesn't need much explanation. I mean, this is what we're all familiar with, is what occurs and what's occurring on the platforms. But this, together with the applications you all have been using, is leading to a very, very large demand on mobile broadband. So I don't know if many of you have had any experiences of dropped calls or issues associated with what's occurring in the network. But as these applications become very popular, there's a fairly significant amount of infrastructure upgrade that needs to occur. And this is really a kind of a summary chart relative to that. And you see the obviously wireless broadband demand preceded cellular mobile, but I think all of us would like to be mobile and bring our internet access and all of our applications with us, even as we go to larger and larger screens. So just as a background, looking in the past, back in the 90s when we went to first the 2G network, it really was built on top of a circuit switch network. And so you had the base station controller, the mobile switching center, which was very circuit switch dominated and time slot oriented. And today, if you're using GSM Edge in your BlackBerry, you still are using the 2G network. Around the 2000 timeframe, the 3G network was introduced, new modulation schemes that many people are familiar with, like WCDMA, but also within the architecture itself, a little bit more of a partition. So this became very much an IP packet over circuit switched or over ATM type of network, and actually is the dominant network rolling out today and being upgraded. You hear many of these names like HSPA or others that are really Node B enhancements for that last segment, really getting to the antenna or the radio access network. The next generation, 4G, which some people are preempting it a little bit and using it in many different ways, really collapses the Node B and the RNC into one device. Well, maybe into one device, but definitely into one box, which they refer to as the enhanced Node B. And this is just starting to roll out in networks like Verizon and a few other places, a lot of trials in Sweden. But all of it is being driven by increasing the capacity within the network to carry more and more broadband data. You'll see a few boxes on the other side, like media gateways, because getting back to the PSTN is still important for some applications, like voice. And so those are introduced into the network as well. Mindspeed's focus was looking at this relative to not just your traditional macro station, which has very broad coverage, uses a very high power transistor, but also as they collapse the cells into what are called small cells in the micro, Pico, and enterprise femto all the way down into the home. And these become important as they try to increase the capacity. One of the issues you have is getting the antennas closer to the user and segmenting and making more and more small cells for where there are congestion points. Congestion points like airports, when everybody gets off of their large Airbus and turns on their cell phone, or other locations like that. So obviously, in doing system on an architecture, our core competencies are built around that. Obviously, algorithms and standards, software verification, software architecture, and traditional packet processing, voice, modem applications, converging those into one SoC. So if we look at the silicon, traditional base stations have been built in a very flexible way, but very agnostic to the application approach, using network processors, DSPs, FPGAs, different types of proprietary in-phase and quadrature, basically IF to RF interfaces, and the back end has traditionally been a circuit switch network. If we look at where the eNode B protocol stack is going, it really is driven by a release of LTE, which is the LTE PHY, MAC, RLC, PDCP. These are all terms relative to the convergence layers that occur between the PHY and getting to basically an IP over Ethernet architecture. So in mapping that, we looked at trying to push this into a very application-specific architecture. So, but relative to that, built on processors so it could be very flexible and retain a lot of the flexibility that you have in the FPGAs and DSPs that are there. So off to the right side, you see that we built it off of Cortex-A9, which is an ARMv7 architecture, along with DSPs from CEVA Corporation and our own proprietary DSP engines and a number of bitstream engines that deal with bitstream processing. So the main goal of this was, of course, relative to costs. The cost per bit to provide to the user all of this data throughput was really something that couldn't be maintained. The network providers really couldn't afford to spend this much money on base stations and provide you with the kind of throughput you want unless an SoC approach was adopted. And you can see these are orders of 10 to 1 magnitude, not only in the cost, but also in the power as well. So this is the architecture. It's a lot of buzzwords that are traditionally used. It is a network on a chip. It is built off of the ARM AXI fabric. Many multi-layer AXI buses in order to basically keep all of the chip intercommunicating with itself. There's a high-performance DSP farm, which consists of CEVA DSPs and Mindspeed application processors. There's a system cluster that has 6 ARM Cortex-A9s grouped as 4 SMP engines and also 2 SMP engines, together with the localized memory and the cipher engines and other aspects. The expansion interface is fairly traditional. A lot of chips have these expansion interfaces relative to DDRs and others. The high-performance SerDes I/O is very specific to the application. That is usually where the radio interface occurs and where the data is moved out to the IF, RF processing. So if we look at the adoption into this chip, we adopted the Cortex-A9 processor mostly for its very high instruction level parallelism. So when we looked at this architecture, it's an SMP 4-core A9 with 32-bit instructions, fairly small L1s, which is fairly traditional at this speed, a little larger L2, and really the ability to do an awful lot of debugging and complex code development on the chip. The CEVA X DSP was adopted as the DSP architecture, mostly driven by its very large parallelism in the data plane, but it does have a significant 8-way VLIW DSP parallelism, at least for the instruction launch. Not necessarily so sophisticated for branch predictions, those type of things, but definitely very good for launching instructions very quickly and doing the math on those instructions. And finally, we added a high-efficiency data level parallelism using a very fine-grained VLIW machine, increased the precision for some of the effects. This is all pretty much a fixed-point machine, so there are some precision effects associated with some of the algorithms that really are pushing you to a little bit higher precision, and so that this is encompassed in the Mindspeed map processor. If we look at this, this is an actual ARM chart, so you can see the high amount of instruction parallelism that occurs in their cores. And then in addition to that, given that it is an SMP machine, there's additional instruction parallelism that comes out of being multi-core as well. The CEVA processors, one thing you notice in this type of diagram, the way it's drawn, is the number and sheer number of banks of memory that are associated with the DSP up on the data plane processing. Down on the instruction processing, it's very wide. It launches instructions very quickly into its pipeline. But really, this is really all about data plane processing in this chip. As far as our thoughts on the application processor, a lot of this was focused around the size and trade-offs of memory and core size, and also comparing that relative to going to some kind of a fixed function signal processor. So if you look at simplifying the instruction set, moving away from dealing with branches as much, and really dealing with the data level parallelism, you get a fairly significant movement of your area into the core itself and away from the associated memories that need to be around it, that are not always associated with the application. And comparing the additional gain we could have gotten relative to a fixed function, we felt in our particular approach that we wanted the flexibility of reprogramming it as opposed to just locking it down to just one or two algorithms that were capable of being executed. This is a look at the inside of this fine-grained VLIW part. It has a 512-word instruction. It's very much like a microprogrammed machine. Pretty simple. It doesn't really have a lot of complexity in its instruction decode, but basically an awful lot of parallelism relative to launching those instructions and dealing with the banks of memory to actually complete the function. Of course, there are some specific things looked at, not only the 24-bit precision that is needed, but types of FFT radix support and other things like that we wanted it to be much more efficient at. In terms of debug, the debug is very much built around the core side architecture from ARM. So you can see here how the trace funnels are all tied together between the 6 processor cores and the DSPs. Each of the DSPs has an on-chip emulation module, and really this allows us to coordinate the debug of development of some of this complex software for the base station. This gives you some trade-offs. If you look at the kind of area in terms of building a chip like this, what are really dominating the area? And I think the one thing that's clear in most chips, and is clear here as well, is it's pretty much memory, memory, and memory. Even inside the cores themselves, their L1s and L2s are a significant portion of the overall size of the chip. You start adding register files and other things, and really a lot of things are dominated by that. You can see that we exchanged some very impressive power numbers, 12 watts in a 31 by 31 millimeter package. There's 26 processors, 9.1 megabytes of SRAM, and greater than 300 million transistors. So now in base stations, as we went through in the beginning, one of the big issues is building multiple size base stations. Well, the very large eNode Bs require more than one of these processors. And they're beginning to require more and more of these chips to intercommunicate with each other as they move into things like LTE Advanced, where you're doing multi-user MIMO and you want to share parameters among different base station components and basically allow one base station to be using the antennas of another base station to try to do interference mitigation relative to users. So along those lines, when we put one of our devices down, we look at how we would actually interconnect them and scale them so that basically you could communicate between them with allowing them basically to share each other's memory space and see what's inside each other's device through a high throughput SerDes interface built around the SRIO interface. Now, in LTE Advanced, they want to do this between multiple base stations. So you could imagine if you have another small base station, you'll have that same interface. And really what we look at there is just extending the interface to optical. So once you get into optical transceivers, which is one of our other product lines, you can start talking about moving from millimeters to kilometers in terms of distance between the different nodes that you interconnect. Okay, now software architecture, sometimes overlooked. This is a really bulletized list of all the standards relative to the 2G standards for data, the 3G standards which came later, built on top of a network, and then finally the 4G. And really this is driving the need for it to be a software architecture as opposed to a fixed function type of product. Now how do we do that? One of the things everyone wants to write in C. I'm old enough to have written in other languages, but most people want to write in C. So all power to them. That's where all the programmers are. So what do? We build a composer tool that looks through and really figures out the dependencies, the resources, and really it's an offline analysis tool that looks at your application, especially around the wireless domain, and figures out how it's going to do the parameterization that's needed for the task scheduler within the device. So this is a kind of a protocol stack view of a radio to router or an eNode B talking to a handset. And you can see that if you're just dealing with layer 1, what we do is we schedule all of the DSP resources below using the ARM processor. And similarly, to execute all of the remaining parts of the protocol stack, we use the remaining ARM processors for there to basically get from what I call IQ to IP. So if you look at a kind of a breakdown of that, here's mapping a PHY. You have a bunch of PHY tasks, whether they be FFTs, forward error correction, interference cancellation, DFTs. And we take advantage of the high level of instruction parallelism of the ARMs, and we map those down to the data plane processing where we have very high data plane processing. So you can see we can basically send to each of these different tasks to be run and complete the PHY channel at layer 1. So we really have an optimized match between the instruction and data parallelism in terms of the execution. Now, that's pretty much, there is other ways of doing the scheduler. I've had other slides before where it's very simple. It's a static schedule. You just basically run one task, and really the only message there is just go to the processor down below. The key differentiators for this product are it's software configurable, which is a mandatory requirement for all of these different types of modems. It supports both Chinese and North American and European standards. Significantly reduces the bill of materials. Very important, it integrates layer 1 and layer 2 on a single SoC, reducing that latency and power between the two different processors. We simplify the programming model for ease of adaptation. And really, relative to our designs, we can scale different versions of these SoCs based on different numbers of processors and different amounts of memory and I/O. Okay, thank you. Any questions? Okay. All right, thank you.
Why don't I start with a question? So how do you decide the balance of the various components of the machine, especially when you have two types of DSPs? How do you decide how many of each type? So you told us how you decided your own design, but how about the balance?
Yeah, if you look at the architecture slide that showed building an eNode B, and there were like 3 of them in there. So the number of processors that we want to put in there are ones that lead to us being able to do the highest processing node of something like LTE in a 2x2 in one SoC. And then we scale from there. So each process generation will put in enough processing to basically be able to do the highest processing, plus most of our customers ask us for 60% overhead.
Can you comment on how you expect this to evolve, like femtocells and where the market's going?
Oh, okay. So in general, the capacity issues that we face require the antennas to get closer to the user. And basically the distance between the handset and the antennas. So there's a couple of different ways of distributing antennas. One is traditionally you can take a base station and you can put remote radio heads. You can put the RF on fiber optic links to different locations. Sometimes they do that in buildings. You can go to Pico cells, which you shrink them down all the way from Ethernet in. And femtocells really is just the smallest version, and it has a lot to do with how many you need and how small you want to go. The difficulty with home femtocells is obviously they compete with Wi-Fi, and there is a lot of reasons why you might argue that home femtocells relative to doing more than coverage for wireless voice might have market challenges relative to rolling out. But relative to an enterprise and trying to get into there, and really providing that type of coverage and throughput, there's a lot more opportunities there. The big distinction, I could say, between all of these technologies and something like Wi-Fi is mobility, the ability to move fast. So for instance, if you had an antenna sitting in a physical location and you tried to use Wi-Fi as you actually try to move fast, the faster you move, whether it be a car or a train, you wouldn't be able to basically maintain your connection.
I had a follow-up question. Are you expecting ARM to add specific instructions to support this market?
So one of the reasons we picked ARM, and we also picked CEVA, was that they are very focused on building their processors for handsets. And handsets are really the market that drives the R&D for LTE PHY level processing. There are a lot of differences relative to an eNode B, relative to the number of channels, number of users, but when you look at modifying instruction set architectures or modifying parallelism, both ARM and CEVA are very focused on making sure that they can do an LTE handset and extending that, selling to us into the infrastructure space.
So are there ARM extensions coming for this?
There are some features of ARM that relative to layer 2 processing could be utilized in the eNodeB. For instance, if you actually look at neon vector permute functions, either byte permute or bit permute, those would actually be very nice relative to doing the layer 2 stacks. When you look, so that's relative to ARM. Now, how far they want to take those type of functions will be mostly driven by the handset, not necessarily by us. Well, there are some that we will take advantage of, but other than that, we will add our own enhancements and features relative to that processing.
Thank you.
If there are no more questions, let's thank Jim again.
All right, thank you.
All right, and we've saved the best for last in the session, so this is going to be the only academic talk in this conference. Nevertheless, a very interesting one for anybody out there that cares about power and energy, which should be all of you. So this is a talk from UCSD. The presenter is Nathan Goulding, and he's going to tell us about this new methodology for building very high performance but very energy efficient chips. The talk is actually titled GreenDroid, a mobile application processor for a future of dark silicon. And I forgot to mention that Nathan is a third-year graduate student at UCSD. He has a couple of bachelor degrees from New Mexico, and he can surprise you with what they are.
Thank you. Good afternoon, everyone. My name is Nathan Goulding, and the title of my talk is GreenDroid, a mobile application processor for a future of dark silicon. This work is in collaboration with my colleagues at UCSD and MIT, Michael Taylor and my advisors Michael Taylor and Stephen Swanson. So today, in this talk, I'm going to discuss three things. The first thing I'm going to talk about is this dark silicon problem. For those of you who don't know, even today, power limitations prevent us from using all of a chip's resources at full speed. Dark silicon refers to the increasing fraction of a chip's area that must remain mostly passive or dark, because in order to maintain the chips, to stay within the chip's power budget. The second thing I'm going to talk, excuse me. In this talk, I'm going to show why this problem is happening and exactly how bad it is, and it's bad. Now, the second thing I'm going to talk about is a way to use this dark silicon in order to make processors more efficient. We convert the dark silicon into specialized cores that achieve up to 11 times energy savings for a mobile application processor. Now, the third thing I'm going to talk about is how my colleagues and I are developing a new mobile application processor that is a better processor for your Android or iPhone. So where does this dark silicon come from, and how dark is it going to be? To address these questions, I'm going to introduce a phenomenon that we call the utilization wall. The utilization wall states that with each successive process generation, the percentage of a chip that can actively switch drops exponentially because of power constraints. This means that each time we move to the next process generation, more and more of the chip becomes dark. Now, we've actually already hit the utilization wall. The problem is already here. And I'm going to demonstrate that using three different sources of evidence. First, I'm going to talk about CMOS scaling theory. I'm going to show our experimental results in verifying this problem, and then show you some observations in the wild. So to start with some scaling theory, under the classical scaling model, for each process shrink by factor S, we see an S squared increase in the number of transistors and a factor of S improvement in device frequency. At the same time, we see a corresponding decrease in power by a factor of S because of lower gate capacitance and a factor of S squared because of lower supply voltage. Now, for a fixed power budget, the utilization of a chip is equal to the product of these terms. And you'll notice that under the classical model, it stays constant. Now, this is great because it means that every time we move to the next process generation, we can still use all of our chip at once. However, this model no longer holds. The transistor threshold voltage is no longer scaling. And as a result, we don't see the S squared benefit of lower supply voltage. Now, as a result, the utilization drops by a factor of S squared with each process generation. This is an exponentially worsening problem. As shown in this graph, this means that the utilization of a full chip drops by a factor of 2 each time we move from 90 nanometer to 65 to 45 and beyond. Now, we verified this in our lab using a real Synopsys CAD flow. We replicated a small data path across a 40 square millimeter chip in a 90 nanometer TSMC process. We found that only 5% of the chip could remain active within a 3-watt power budget. Moving to 45 nanometer, this number drops to just 1.8%. And ITRS roadmap projections predict another factor of 2 decrease in moving to 32 nanometer. Now, we've also seen evidence of this in the wild. Processor frequencies are no longer scaling like they used to. And in fact, the frequency curve has tipped over since about 2005. As another example, Intel's Nehalem architecture includes a turbo mode in which some of the cores run faster when the remaining cores are switched off. Finally, we've also seen an increase in cache to processor ratio in new chips as more area is dedicated for the lower activity cache compared to a higher activity compute logic. So the utilization wall is here. We've seen evidence of it, and scaling theory says things are just going to get worse. This is a huge problem. The utilization wall is going to change the way that everyone builds processors. Pretty soon, our chips are going to be full of dark silicon. So what do we do with this dark silicon? Well, a couple of insights stand out. First, power is now more expensive than area. So if we can trade area for reduced power, it's a win overall. Second, specialized logic can provide orders of magnitude improvement in energy efficiency. Our approach is based on these insights. We fill dark silicon with specialized cores to reduce the energy on common applications. As I'll show later on, these cores include a patching or reconfigurability mechanism that allows them to handle changes to the software. Our approach is called conservation cores because they conserve energy. Conservation cores, or C cores, are specialized circuits for reducing energy in target applications. As shown in this diagram, C cores sit alongside a general purpose processor and share the same data cache and memory hierarchy. Hot code, which is frequently executed code, runs on the C core for greatly reduced energy. Cold code, such as startup and teardown or infrequently used code, runs on the general purpose processor, and execution transfers back and forth between the two. Now, we generate C cores using a fully automated toolchain. The toolchain generates synthesizable Verilog, and at the same time, integrates C cores into the software. It does this by inserting function stubs into the application that call the C cores during runtime. C cores are extremely energy efficient. They can provide up to 18 times better energy efficiency for the code that they target compared to a general purpose processor. Now, C cores provide an architectural way to trade a cheap resource for an expensive one. In this case, area for power. So now let's take a look at the life cycle of a C core. C cores start with a set of applications that we're interested in. We pass these applications through our compiler, which profiles and extracts the energy-intensive code regions for conversion into C cores. We generate the C core hardware and use it to fill the dark silicon of a many-core processor. Now, over time, the software may change as new versions are released. Our compiler is able to look at the difference between multiple versions to generate patches that allow old C cores to run the newest version of the software. This allows C cores to remain useful even in the face of software changes. Okay, so I've introduced conservation cores as one way to leverage dark silicon to scale the utilization wall. In the remainder of my talk, I'm going to discuss GreenDroid, a mobile application processor that we're developing at UCSD. I'll show you the GreenDroid architecture and our work in developing a prototype chip. Then, I'll describe conservation cores in more detail and show how they can provide energy savings for even irregular integer programs. Finally, I'll return to GreenDroid and show its projected energy savings and wrap up with some brief conclusions. But first, in order to better understand GreenDroid, let's take a look at some emerging trends. Well, the utilization wall is exponentially worsening the dark silicon problem. Because of this, specialized architectures are receiving more and more attention because of the energy efficiency that they provide. Now, at the same time, mobile application processors are becoming a dominant compute platform for many end users. This graph plots Android and iPhone sales data versus Dell computers for the last 3 years. It also shows projections for the next year, and you can see that smartphones are taking off at an exponential rate. Now, another interesting trend is that the evolution of these mobile application processors is mirroring that of microprocessors. This graph shows a timeline of architectural features added to Intel and ARM processors. Looking at the blue line, we start with the pipelined 486 and move to superscalar, out of order, and now multi-core designs. The red line shows how application processors are progressing along a similar path. Now, unfortunately, these application processors also face the utilization wall because of their growing performance demands and the extreme power constraints of the embedded design space. Now, what are people using these mobile application processors for? Well, one example is Android. Android is Google's operating system and application environment for mobile devices. This diagram shows the Android software stack running on typical hardware. Applications are written in Java and compiled to run on the Dalvik virtual machine. The applications also call into a set of shared libraries, including libc, OpenGL, and many others. Now, this software model actually makes Android a great fit for conservation cores. This is because an Android smartphone runs a core set of commonly used applications. For example, a web browser, an email client, and various media players. Now, these applications rely on the Dalvik virtual machine and the shared libraries, making this part of the software stack particularly hot code. We can also target specific hotspots from certain applications and the Linux kernel. And we can convert all of these hotspots into conservation cores for great energy savings. Now, Android is great. There's another reason that Android is great for C cores, which is the relatively short replacement cycle of handsets. Most consumers replace their phones every 2 to 3 years. We can continually develop new C cores as more applications appear and become popular. At the same time, the C cores interface allows us to remove C cores at any time without affecting backwards compatibility, because the applications can always fall back to the general purpose processor. So to quantify these benefits, we constructed a workload of common Android applications. We profiled this workload to determine how much code we would need to convert into C cores in order to achieve good energy savings. This diagram shows the percentage of dynamic execution coverage that we can achieve versus the number of static instructions converted into C cores. Now, we divide the C cores into 2 categories, targeted and broad-based. Broad-based C cores are C cores that are shared by 2 or more applications. Looking at the hottest 40,000 static instructions, we find that 72% of this code is actually shared by more than one application. That makes it ideal to turn into broad-based C cores, which can be used by multiple applications. Now, we can also create C cores that are targeted for a specific application. Adding targeted C cores to the mix, we can achieve 95% of execution coverage with just 43,000 static instructions converted into C cores. This is the equivalent of about 7 square millimeters in a 45 nanometer process. So now I'd like to introduce GreenDroid. To construct GreenDroid, we take a number of Android workloads and pass the applications through our automatic C core generator. This automatically generates the hardware for the C cores, which we use to populate a tiled multi-core lattice. So let's take a look at the architecture. GreenDroid is a tiled lattice consisting of 16 cores. Each tile contains between 6 and 10 Android C cores that share a 32K D cache with a MIPS general purpose processor. The MIPS core is a 32-bit in-order 7-stage pipeline with a 16K iCache and a single precision FPU. Now, each tile also contains an on-chip network router that allows it to communicate with the other tiles and off the chip. Now, let's zoom in on one tile. This floor plan shows that each tile is a square 1 millimeter to a side. Half of the area is dedicated to conservation cores. In the center, you can see the shared data cache, and the remaining area is dedicated to the MIPS core and on-chip router. Now, we've implemented a tile skeleton using a 45 nanometer process targeting 1.5 gigahertz. You'll notice on the right side is a large blank area. This area will be filled with C cores, and each tile will contain a different set of C cores. Okay, so we've seen a little bit about GreenDroid. Now let's take a look at the heart of our solution, conservation cores. We'll start by seeing how conservation cores are built. So C cores start with application source code. But unlike most accelerators, they can target irregular integer programs because C cores are parallelism agnostic. Our toolchain supports almost all of the C language, including complex control flow, goto and switch statements, and even function calls, arbitrary memory structures, and arbitrary operators. Now let's walk through the progression of a simple example. The code shown on the right sums the elements of an array. let's convert this code into a C core. So the process starts by profiling an application to determine the execution hotspots. We convert these hotspots into an intermediate representation from which we generate synthesizable Verilog. The diagram on the top shows a representation of our sum array example. And you'll notice that there's a control unit and data path that directly map from the control flow and data flow graphs of the original program. Now, at this stage in the process, our compiler also inserts architecturally visible scan chains. These scan chains allow us to access the internal state of a C core. And I'll show later on how we can use this mechanism to support arbitrary changes to the code later on. Now, after we generate the hardware in Verilog, we process the Verilog in a 45 nanometer Synopsys CAD flow. This takes the C cores through place and route. And as you can see, this is the final product of our sum array C core. It synthesizes to just 1/100th of a square millimeter and runs at 1.4 gigahertz. So that's how we build C cores. Now let's take a look at how they perform. We used our toolchain to automatically build 21 C cores for 9 hard applications. And here, hard applications includes irregular integer code, including some from Spec Int 2000 and 2006. We generated these C cores using a 45 nanometer TSMC process, and they vary in size from 1/10 to 1/4 of a square millimeter. So this graph shows the energy efficiency of C cores for non-memory operations compared to a baseline MIPS processor. As you can see, the C cores are up to 18 times more energy efficient and more than 13 times on average. Now, this energy savings is great. Where does it all come from? The pie chart on the left shows a breakdown of the average energy per instruction of the MIPS processor. Over half of this energy is wasted in overhead, including the iCache, the fetch unit, and the global register file. C cores save this energy because there aren't instructions. They've been converted into hardware. And instead of a global register file, we just instantiate registers throughout the data path as needed. Now, the MIPS processor also has a inefficient general-purpose compute pipeline. We can reduce this energy by using specialized functional units and bit-level optimizations. Now, energy saving, we've seen that special-purpose hardware can achieve great energy savings. But what happens if the software changes? Well, a downside of some hardware solutions like ASICs is that if the software changes, say there's a bug in the program or a protocol changes, the hardware becomes useless. C cores, however, can support changes, arbitrary changes to the code using 2 methods. First, C cores are unaffected by changes to the cold regions because these already run on the general purpose processor. But secondly, C cores can also support arbitrary changes to the hot code. They do this through 3 different patching mechanisms. We can support arbitrary changes through a software exception mechanism, which I'll describe shortly. But there's also a couple of special cases that we can optimize for. We can replace program constants with configurable registers that we can set at program load time. We can also replace fixed operators with configurable functional units. For example, replacing a fixed adder with an add-subtract unit. Now, as I mentioned, we can support arbitrary changes through software exceptions. This means we can basically pause execution in the C core, transfer control to the general purpose processor, and the processor will use those scan chains I mentioned earlier to retrieve any values it needs or state from the C core. The processor will execute whatever software it needs and scan the values back out to the C core where it resumes. Now, using these patching mechanisms, we can greatly extend the useful lifetime of our C cores. This diagram plots the energy efficiency of C cores that are normalized to a MIPS processor over time as different software versions are released. So if we focus first just on the top graph, this is for non-patchable hardware. And looking at the top line, this represents MCF 2000. Now, you'll notice in the year 2000, we can start executing MCF on our hardware, and we achieve great energy savings. But in 2006, a new version comes out, and we lose all of the benefit because we have to run on the MIPS processor. We see a similar trend with 4 out of the 5 benchmarks that are shown here. Now, if we look at patchable hardware, which includes those mechanisms I just described, again, look at the top line, and we see MCF. We only lose a little bit of energy efficiency, in moving when the new version is released. And 4 out of the 5 applications remain useful even as the new software appears. These patching mechanisms greatly decrease the risks commonly associated with specialization because the hardware remains useful even when the software changes. Okay, so I've shown you how conservation cores can leverage dark silicon to achieve great energy efficiency. I've also shown how patching mechanisms allow the C cores to remain useful even as the software changes. Now, let's return to GreenDroid and see how C cores will save energy on an Android workload. Now, in order to save the most energy, an application must run on the C cores instead of the general purpose processor as much as possible. As we saw earlier, we can achieve this by dedicating more silicon area to the C cores. Effectively, the more area we have for C cores, the lower the energy requirements of the workload, which goes back to what I was saying earlier about trading area for power. Now, using our workload, we were able to model the average energy per instruction of our GreenDroid processor. This graph plots the results. You can see on the left side, starting with no C cores at all, the baseline processor uses 91 picojoules per instruction. But adding just a few C cores quickly drops this energy. And we find that 7 square millimeters of C cores provides 95% execution coverage and 8 times energy savings compared to the baseline. Now, we've used our workload to identify some candidate hotspots in the Android source to convert into C cores. This list is sorted by the execution coverage shown here in this column. So at the top of the list are a couple of functions from the Dalvik virtual machine. The Dalvik incorporates, or at least these functions incorporate 14.4% of execution. And it's important that we cover these because every application uses them. We also see some functions from the 2D graphics library libskia, covering 8.4% of execution in our workload, and some memory management functions from libc, covering almost 7%. Now, we can convert all of these functions into C cores and many more. So now let's compare GreenDroid to a typical mobile application processor. For our baseline system, we're assuming an aggressive application processor running at 1.5 gigahertz in 45 nanometers. We conservatively estimate this processor to run at 91 picojoules per instruction, including compute energy and data cache access. Now, we can measure the C core power using post-place and route gate-level simulations and Synopsys prime time. We've measured C cores to use just 8 picojoules per instruction for a savings of 11x compared to the baseline. Now, cold code has to run on the general purpose processor. At 95% execution coverage, we can still achieve 12 picojoules per instruction in the C core in GreenDroid. This is approximately 7.5 times better than the baseline system. So now I'll tell you about the project's current status in developing a prototype chip. We have already generated a toolchain that automatically creates C cores from source code and takes them through place and route. We also have a cycle and energy accurate simulator of the C cores and the tiled lattice. In addition, we have FPGA emulation of C cores and the tiled lattice. Now, ongoing work includes finishing the full Android system modeling so that we can get a more detailed picture of the workload. We can use this better workload model to finalize our selection of C cores. And then we can complete time enclosure and tape out. So a few conclusions. The utilization wall forces us to change how we build hardware. Conservation cores use dark silicon to attack the utilization wall. GreenDroid will demonstrate the benefits of C cores for mobile application processors. And we're developing a prototype chip at UCSD. Thank you, and now I'd be happy to answer any questions.
So, courtesy of the previous speakers, you have plenty of time for questions.
Mark Tremblay, Microsoft. I have a couple of questions. First one is, what is the typical granularity of the code you map onto the C cores?
So we can map anywhere from a few basic blocks to a loop to a function. Ideally, C cores cover loops because we spend more time there. But if there's a large block of irregular integer code, we can convert that into a C core as well.
And does the MIPS CPU coordinate all the starting the C cores and identifying where the registers are and what part of the cache to use and so on?
So the C cores share the exact same cache as the MIPS processor. And they just use the same addresses, they make the same requests as the MIPS processor. The MIPS processor is in charge of launching C cores.
Right.
That's
So the assumption is that the MIPS processor is off while the C cores are running. Right?
Actually, it could be off. You could say, okay, go and run, or you could run some other thread and wait and say, you could think of the C cores as a helper thread.
But in your math here, you're assuming it's off. Right?
That's correct, in the numbers we've shown.
Thank you.
Peter Teshin, Naval Postgraduate School. So is there a possibility of doing this in an FPGA rather than an ASIC? And it won't run as fast, but...
Yeah, so we already have some emulation in an FPGA, and so that would work as well, definitely.
So the dream is finally here, we can have an FPGA-based PDA?
I'm sorry, I missed the question.
I said we can finally have an FPGA-based PDA now?
Yes, definitely.
Alex Lomatnikov, HiCam Systems. So in your numbers, you said you don't include memory system. So is it just the core?
So
would you comment on the full system power when you?
Yeah. So the numbers I showed with 8 picojoules and 12 picojoules, that's including data cache access, text to both the MIPS processor and the C cores.
Okay, and another question I have is, Tensilica has a technology called Express compiler for a while now. Could you comment on what you do differently from the existing technology?
Yeah, so that's a great question. C cores can target any irregular code that you throw at them. I'm not entirely familiar with Tensilica's Express. But perhaps, like I said, C cores can do basically arbitrary code in an automatic fashion. So we see benefits in that way.
Todd Besnick, Quantum. Sorry, I'm reading my email while I ask your question. Is there any particular reason you picked MIPS over ARM? I saw you had ARM in your ramp up of new architectural ideas. So
this technique would certainly work with ARM as well.
That's not what I'm asking. I'm asking what's the driving force behind picking MIPS?
Oh, we already have access to some of the MIPS core, and so we've just been using that and building on that.
So are you partnering with MIPS?
We have not discussed that yet.
Okay, thank you.
Yes, Brian Holden, Hypertransport Consortium. Presumably, you could also have some knobs you could tweak one or the other to increase the performance of certain sections at the expense of energy using the same sort of flow.
Certainly, yeah, that's a great idea.
Hi, I'm Michael Adler from Intel. You estimated 10 years for the lifetime of some of these cores for the software running on them with modifications. I wondered how you came to that number.
Yeah, so that was using some applications from another set of benchmarks. Those were mostly spec applications. We would need to do a similar study for Android applications, but as I mentioned, the replacement cycle is much shorter, so there's less risk involved in software disappearing.
The spec doesn't change very much.
We noticed differences in even the input format that we were able to handle, for example, with VPR. But you're right, we would have to do more of a study to see software applications in Android. Thank you.
Derek Sharma, University of Waterloo, Cisco. You mentioned for the spec and performance, but did you have anything for Android? I mean,
I'm sorry, can you repeat the question?
You had the performance for the spec benchmarks. Did you have any sort of performance results for Android libraries?
We're still working on that. We have preliminary results, but not enough to display at this time.
For something like the JIT, or at least the VM Delvic, or functions there. I mean, I'm thinking if they spend a lot of time there, but if it, for irregular integer code, if it goes in and out of them. I'm thinking, I mean, the back and forth between the main processor and the C cores, it'll end up like, I mean, you know, like bad performance. I mean, what?
Right. We have the interface between the MIPS processor and the C cores is small, but there is an overhead. So we would clearly or carefully profile these applications to make sure we're building the right C cores so that we're not wasting this time in overhead going back and forth.
Okay, thank you.
This is CC Yuan from Huawei Technologies. I have two questions about your C core. First is for any specific application on your SoC chip, those C cores must be on the same type, or they can be of a different flavor, just distribute through the chip?
So according to the application workload, we can distribute the C cores or even replicate them across the tiled architecture. You can imagine execution transferring from one core to the other around the chip as necessary if certain C cores are not available. Additionally, if a C core is in use by another application and there's not a duplicate available, the application can always default to running on the MIPS processor just without the energy savings.
So that implied it's certainly possible for certain SoC you have different flavor of C core mixed in one chip.
I'm sorry, we have a different...
So you can hybrid, you can have heterogeneous C core in one chip for different accelerating computing.
Yeah, definitely.
The other question is, it's to follow up Mark's question, when the MIPS core is off, can the C core communicate each other?
That's a great optimization that we haven't implemented yet. But there's no practical reason why we wouldn't be able to transfer execution from one C core to another.
Well, it's not transfer. It's like when the algorithm is evolution, and in certain case, your C core is just, the capacity of the C cores cannot handle all the computing, even by configured. So you have to kind of increase its capability. So if you can vector the C cores together, you have much higher power without changing anything. That's why I'm asking, can the C core talk to each other directly?
Oh, they certainly would be able to we haven't implemented that feature yet, but they certainly could. There's nothing to stop them from doing that.
Thank you.
So surprisingly enough, we have time for my questions. So I guess follow up on Mark's question, what's the memory model that the C cores see? And I'm curious both about virtual memory and multi-processor ordering.
So the C cores, as I mentioned, share the exact same data cache as the baseline processor. And so they make requests to the same memory controller.
So if I get a virtual memory exception in the C core, what happens?
That's a good question. That would probably trigger an exception in the MIPS core, which could handle the exception.
I guess the other question is that you saw that, just by using about, doubling the area of the core, you can add all the C cores and get these great benefits. But, you started your talk by saying that every generation of CMOS technology will have twice as much dark silicon to use. So, okay, we do the C cores. After that, what?
So we can add more and more C cores as we get more and more dark silicon. We can actually just start targeting sort of esoteric or infrequently used applications. Right now we target the hottest code, but there's no reason we can't target more and more of the workload. We also, looking at some of the emerging trends, we're sure that these mobile application processors are going to take off, and there's more and more we're going to want from them, just as we saw with microprocessors. Good question.
That means that people will be writing code at exponential rates? Oh, I'm joking. So let's thank Nathan.